Hey, good afternoon, everyone. We're very happy today to have Martin Weides, who's a professor of quantum technologies at the University of Glasgow and the director of the James Watt Nanofabrication Center, where he leads UK first efforts in CMOS-compatible superconducting quantum device fabrication. He's held research and faculty positions at leading institutions, including the Karlsruhe Institute of Technology, NIST in Boulder, and UC Santa Barbara. He's a graduate of the University of Cologne, where he has driven quantum hardware advances across Europe and the US. So we appreciate him joining us across time zones today, and I'll hand the floor over for a talk on superconducting quantum hardware. Thank you.
Okay, thanks, Chris. Thanks so much. So I will then just kick off. Actually, I'm happy to take questions whenever they arise. I might not, so if you raise your hand, I might not see it, so maybe just speak up. Um, so, well, today, yeah, I would like to talk about superconducting quantum hardware. That's what you do here in Glasgow. And well, Chris already gave a fantastic introduction into, I guess, our research and bit of history. So I'm working at the James Watt School of Engineering here in Glasgow. That's in Scotland, UK, in the upper part of that island. Um, so my research group is a quantum circuit group working on superconducting quantum devices such as yourselves. But I'm also the director of our clean room, the James Watt Nanofabrication Center. Um, and actually down here you see a picture from about 2 years ago. We moved into a new building, the Advanced Research Center. Now we have four, soon five PIs, academics working on superconductors here in Glasgow. So that's Kaveh Del-Fanasari, it's Robert Hetfield, and Jaime Macedo, who's also working on spin systems and spintronics, and myself. So in total, we have about group, I think, of 30 plus postdocs and PhDs with, in terms of cryogenics, two dilution refrigerators. Soon there will be four, so two more are coming. We have an ADR down to 50 millik. We have some 300 millikelvin system, and then actually a lot of 2 Kelvin, 3 Kelvin systems, which are mostly used in Robert Hetfield's research, who's working on single photon detectors. Kaveh Del-Fanasari works on hybrid super and semiconducting structures. Jaime Macedo on superconductors and spintronics, and myself, I have a really background in Josephson junctions and superconducting circuits, but I'm also moving into other areas, and I will tell you a bit about that. Now, in Glasgow, we have a large center or a large activity, part of the Center for Quantum Technologies, and that was actually what brought me to Glasgow in 2018. So over the last 10 years, prior to my arrival, actually, over the last 10, 15 years, we've been contributing to the UK quantum technology program. So we have a large research portfolio, number of publications. Actually, most of the work we do is more in optics and photonics. I mean, superconducting is a growing activity, but the real strength is in photonic systems, also in semiconductors in 3.5s, and in quantum optics in particular. We have been leading and are leading quantum technology hubs, are contributing to the other quantum technology hubs which we aren't leading, and we also have close links to the National Quantum Computing Center, which is now set up near Oxford. So in terms of numbers, we have about 100 plus researchers in quantum technologies, with a strong focus on enhanced imaging, quantum imaging, also sensing and timing, and also position navigation timing is a large activity. Quantum computing, we also do, particularly superconducting, and then also quantum comms. And that's supported by Quantum Foundry, which is our clean room. And we have another team in physics focusing on on quantum science and the fundamentals of quantum technology. Now, the clean room, because our work lies a lot in the clean room, so I would like to introduce that. It is actually in a very interesting location. It's sitting in a Victorian building, so you don't see much from the outside. It is fairly large, so it has a footprint of about 1,200 square meter. We have fairly large team of staff, technicians, and research technologists which support us. And then we have about 200 members which are coming out of the university, but we also have industrial access. I assume similar to Berkeley's clean room. It's probably similar to the Santa Barbara one, which I at UCSB, which I know quite well. And well, we do the clean room supports some variety of technologies, so photonics and lasers and photon detectors are a large part of the waveguides, are a large part of the activities. We're also building ion traps and cold atom cells and super and semiconducting qubits. You can also go for a tour if you wish. There's a link, a 360 walk through the facility. Now, Glasgow is part of Scotland. We have a number of strong universities up here. And particularly in quantum, we collaborating closely with Strathclyde, who are also here in Glasgow, and the University of Edinburgh. A few years ago, we formed the Quantum Computing Application Cluster, QCA, which supported by Scottish government. And in there, we are covering three major qubit hardware platforms. So we have neutral atoms at Strathclyde, we have superconductors at Glasgow, and also semiconductors, which are pursued both by Strathclyde and Glasgow. And we also have a large activity, actually, even strongly growing activity on software, where we look into applications. That's predominantly at Edinburgh and at the High Performance Compute Center there, the EPCC. And we also do benchmarking, testing, verification. We do look into quantum programming languages, compilers, and emulation work. So that is kind of sets say the scientific background and base for our activities. Now, in my talk today, I would like to talk more about what actually I'm doing. So I've chosen three topics. So the first activity is niobium qubits, so to move away from aluminum superconducting qubits, but to some different structures, such as niobium. Then there's an activity on nanobridge Joseon junctions, also for qubits. And we have an activity on interfacing cryogenic quantum technology, quantum computing. That's more the classical part of sending from Schwall and Wheeler signals down into the cryogenic system and getting it back. So I probably don't need to introduce superconductors and superconducting qubits to this audience. I have this slide here, but I will be really quick. So for superconducting qubits, we're using conventional superconductors, metallic superconductors, which are characterized by superconducting gap, separating the superconducting condensate and the quasi-particle band. Now the qubit frequency, the qubit excitation, has to be smaller than twice the superconducting gap. And that's to avoid the formation of quasi-particles when we control the qubits, when we send microwave pulses onto the qubit. We have to ensure that we are not pair breaking the condensate. And that's one requirement. The second requirement is the thermal environmental energy of our chip and the package needs to be smaller, much smaller than the qubit energy or the qubit frequency to avoid thermal excitations. And that means if you use, say, aluminum as a superconductor, a qubit frequency on the order of 5 to 10 gigahertz is very convenient. That's low enough to avoid the formation of quasi-particles, but it's also high enough to avoid a thermal population of the qubit itself. And also aluminum as a material is easy to deposit and to structure into quantum circuits, and it's the leading superconducting technology. Particularly the junctions are almost all of them are formed out of aluminum oxide, aluminum layers. Now, these low temperatures of 10 millikelvin are achieved using dilution refrigerators, as I'm sure you all very much aware. That's a multi-staged cryostart. Here's one example there. They're different vendors, but they're all very similar in terms of functionalities. So the lowest stage is of course down there, 10 millikelvin. Then there are higher temperature stages which provide pre-cooling, and the cooling power is given in this table. So at 4 Kelvin, there's about 50 watts of cooling power. At 3 Kelvin, it's 1 watt. And at 100 millikelvin, it is on the order of a milliwatt or less, typically. And then at 20 millikelvin, it's just a few microwatt. At 10 millikelvin at base temperature, there's no cooling power, obviously. That means all the signals to control and to read out the qubit have to come in from the outside. These are coaxial wires which go into the system, and these must be well thermalized, and a lot of care must be taken that there's the quarks are really cold, and you're not introducing additional heat into the system, which would then pull up your base temperature. Scaling is a challenge. It's a true challenge if you just think of brute force scaling by adding more coaxial wires to the quantum processing unit. Then there will be limit. Here's an example for the passive heat load through the quarks for about 1,000 quark system, and you see that the cold plate is already at half the cooling power, the 4K stage as well. Now this could be increased, but there are the significant engineering challenges as well. It is also a very manual process of adding all these coaxial wires. So we think for scaling further to a million qubit or beyond, it would need different solutions than just adding coaxial wires with all control electronics sitting at room temperature for quantum computing. Here's a work we've done, a paper and calculations we've done during lockdown. So it's predominantly numerical work. So we looked into such a cryostart, for example, and looked into a coaxial line, which goes from room temperature all the way down, and then looked into the mode attenuation, actually the mode propagation of microwaves at the fundamental mode, but also at high frequencies, and then looked into the noise photon flux through this single coaxial wire, which has a certain length and has some attenuation. And we looked into the photon flux, which is brought actually onto the millikelvin stage here in blue. It turns out it's actually quite a lot. At least if one just uses the quarks itself with conventional attenuation without echo Sorb filters. And it also turns out the physical length of that quarks matters quite a lot, which could explain why at times it's challenging to reproduce qubit measurements in different fidgets, because the coaxial wire itself might be a bit different, and you end up having different effective residual photon flux down to the quantum stage, which then will cause decoherence of the qubit system. So, but maybe zooming out again and talking about motivation. So there's a lot of the last 10, 15 years, there's been a lot of activity, lots of progress around and within superconducting qubit technologies. I mean, here are just some fairly recent achievements. So Google has been demonstrating quantum advantage, quantum supremacy more than 6 years ago, and then this has been for different applications has been also demonstrated by IBM and by D-Wave on their annealing system. Google has then, and Zurich and others have demonstrated an error-corrected qubit. The first publication is actually a few years ago, and then there were more in recent months. There are a number of roadmaps for their technology, industrial roadmaps out there. So the next really major goal is realizing 1,000+ qubits, which are based at 4 to 8 gigahertz and operated at 10 millikelvin. So the gigahertz frequency is, I already talked about it a bit before. It's chosen, I think, for a number of reasons. First, it works really well for aluminum-based qubits and tunnel junctions. Having gigahertz frequencies means the wavelengths are fairly large, so designing a circuit and a package is easier. One can also rely a lot of 5G and 4G, 5G microwave technology to build the control system. Microwaves also have a fairly large mode volume. That means actually coupling these microwave modes couple less to single atomic defects. That helps improving the coherence. The control electronic is fairly standard, so one can use off-the-shelf components. Maybe the downside to having such low frequencies is the shielding requirements are massive because the qubit energy is fairly small. So the qubit needs to be put in a dark state or the dark in a dark system, so avoiding any higher energy radiation hitting the sample, and that needs then a lot of engineering to really ensure that no stray light hits the sample. The roadmap for the next 5 to 10 years envisions 1 million+ qubits, but it is not so simple to scale up the cooling power, which is about 1 milliwatt at 100 millikelvin. Maybe that can go up a bit, but so if the community stays at a few gigahertz qubits, then and still relies on the conventional way of bringing signals into the cryo state and out, there are many challenges ahead. And in our research, we're looking into some of them and hope to find solutions. So this slide introduces the Joseon junction, which I think I don't need to introduce really to this audience. So Joseon junction is formed when you have two superconductors separated by a thin oxide, a tunnel junction. There are the two Joseon equations for the DC and AC case. And you can also, if you do a bit of math, you can also then form a Joseon inductance, which means the Joseon junction forms a point-like nonlinear inductance. And that is the core element to form superconducting qubits, at least if you refer to transmon systems. So a superconducting qubit is formed by first taking an harmonic LC oscillator, just a capacitor and a geometric inductor. That system has a harmonic potential with equidistant level spacing. And then in the simplest version, we just replace the geometric inductance with the Joseon junction, with one Joseon junction. And the nonlinear property of that Joseon junction then leads to a non-harmonic to an anharmonic potential, meaning the level spacings between the ground and the excited, the first and the second state, are different in frequency. And this forms a transmon qubit, which is nowadays predominantly used. One can also replace one junction with two junctions, so just forming a split junction, and then using an external magnetic flux. The inductance can be changed, can be varied, and that means the qubit frequency becomes tunable and can be controlled through an external current or an external flux to the system. Okay. These Joseon junctions along capacitors, inductors, and split junctions form a really rich toolbox to build arbitrary quantum circuits. So qubits and B-dot elements and couplers between the qubits. And here, for example, is is a resonator, actually a readout resonator. We did in our group a while ago. So it's a lumped element resonator. We have a capacitor. We have an inductor here on the left that's coupled to transmission line, and then this feeds further on to qubits, and that's done in many groups. Um, so the design is fairly simple. And can be adapted for the specific needs. Here I would like to show you one work from 2 years ago we did on quantum simulation. It's a bit non-standard, so I thought maybe that's interesting. So what you see here is we formed a qubit, which has this funny shape. So there are these two, well, half circles forming a capacitor. There's a split junction in here. You probably can't see this, but on the bottom, sorry, on the top left, we have a split junction. Now, so this red obstacle forms our transmon qubit. It's controlled by a flux bias coming here from the top. It is coupled to readout resonator, which sits further on top. And then it is also coupled to four, actually five, but one didn't work, to four fixed frequency resonators, which are all at slightly different frequencies. The Hamiltonian for that system is up here. Now this system forms a multi-state Landau-Zener system. So we have our qubit. Here we have our set of fixed frequency resonators, and then we have a coupling term. In addition, we also have a control line to the resonators, which then allows us to either ring up or read out these resonators separately, independent from the qubit. And we use that actually to ring up these resonators, and then use the qubit to infer their state. So the motivation behind that experiment was to study the multi-state Landau-Zener model in depth. I mean, the conventional Landau-Zener model has been studied, I think, many times, but we wanted to study actually a bit closer. So, and the Landau-Zener model, why it's interesting, is shown here on this slide. So if you have the qubit in excited state, and it's sitting in frequency below that bosonic bars, so these resonators, and then if we increase the frequency, so if you then sweep the qubit past that bars of bosonic modes, we will couple to the resonators, and we can lose excitation. So the excitation can swap from the qubits to the resonator. Now the probability of swapping to the resonator depends on the Landau-Zener velocity, which is the frequency with which we are sweeping past these resonators. So if we are changing the qubit frequency really quickly, then it wouldn't really couple to the bosonic bars, and we would maintain the one state, the qubit excited state. But if we were to sweep really slowly, then the quantum state would adiabatically go from the qubit onto one of the resonators. And then after we completed the sweep, we can read out the resonator and read out the qubit and determine its final state as function of the Landau-Zener velocity or other excitations in the system. So here's a measurement scheme. We first started with a qubit in ground state, excited it, then changed its frequency by then sweeping it past the resonators. The Landau-Zener frequency is set by the rise time and the difference between initial and final frequency of our qubit. And then in the end, we did read out to infer the qubit state. So here is the first measurement along with numerical simulations. if if we follow this trace here, um, now the color code is inverted. So light blue means the qubit is excited, dark blue means the qubit is in ground state. So if we sweep the qubit really quickly past the resonators, it stays in one state. There's a bit of decoherence, but it predominantly stays in the excited state. If on the opposite, if we sweep it really slowly past the bosonic bars, we swap the qubit excitation into one of the resonators, and it enters approaches a ground state. If you look into the data in between, there are some oscillations, so we have some interference because every time we are sweeping by a resonator, we are changing the phase of our quantum state, and that leads to constructive or deconstructive interference, which is seen in the experimental data and also in the numerical analysis. So this on this slide, you see the same data. These are just line plots along these, I think, 5 different sweep times, along with simulations. It's really the same data as on the slide before, but for visualization, it's perhaps useful. So if you build a full numerical model of our system, the numerical data captures experimental data quite well, including the oscillations and the decoherence which comes from both the qubit and the bosonic bars. So we think there's a nice agreement between experimental data and our numerical model. Okay, we can also do a similar experiment, but now having the qubit in ground state, but exciting one of the resonators. Here's data where the first resonator, the one at lowest frequency, was excited, and the results are very similar. So if we sweep really quickly past that excited resonator and all the other ones which aren't excited in this experiment, so if we sweep it quickly, we don't really pick up a qubit excitation. So the qubit stays in the ground state. However, if we sweep slower or really slow, then we start picking up, we couple and we pick up excitations from the resonator. And again, we see destructive and constructive interference once we have picked up the excitation state of that system. Now, on the right, you see numerical simulation as well. And again, there's a fairly good agreement. Now the quantum chip itself, this one, I showed it here, it didn't have a great coherence. So I think there was about a few microseconds at best, which meant, and then implementing the sweep took some time. That means we already had actually significant or not insignificant decoherence within the qubit itself, and that kind of washes out some of the features in the experimental work. Now, I think it's a very interesting experiment because what this allows you, and if you were to scale it up to larger numbers and higher coherent systems, you can actually probe and emulate the dynamics of open quantum systems, also reflecting the high number of states in each of these resonators, which could be populated really high quantum states with coherent states or with Fock states or perhaps with a mix and maybe of the thermal states. And then you can actually probe this and its impact on your qubit or your qubit system. Okay, I would then like to move on. Happy to take questions if there are some.
A good place to pause. Does anyone have a question? Feel free to unmute yourself. Anything? All right, I guess not at this point.
Okay,
If something does come up, please go ahead and unmute or put it in chat, and we'll get your question answered.
okay, that's fine. So then I would like to move on. So here we did a very simple experiment. We've taken a qubit, a fixed frequency qubit coming from NIST, and we probed that over long time scales, over hours, and we measured it again after warm up and cool down. And we looked into the stability of our qubit frequency and also of, sorry, there was, yeah, T1 and T2 times. And here you see a typical plot. So the qubit frequency or the change in qubit frequency is plotted in blue. And you see that fluctuating a bit. And you see a lot of fluctuations in T1 and T2 times. And that, I should say, also has been observed by many other groups. Ours was one of the first ones, but there's a whole body of similar work nowadays. And you can also take the data and calculate the power spectral density. For example, here we would see, you would expect a 1 over decay, but what we see is this 1 over decay plus some Lorentzian with, in this case, a frequency of 1 millihertz, and that causes these fluctuations in qubit frequency, these almost telegraph noise jumps in frequency. Now these dynamics are caused by TLS, by two-level systems, which are coupled to the qubit. They are weakly coupled, but they're coupled to the qubit. The TLS themselves are sitting at fairly high frequencies, but they're coupled to two-level fluctuators sitting at lower frequencies, likely being thermally excited. So we have these thermally driven two-level fluctuators, which then once in a while kick the two-level system, and the two-level system, that atomic defect will impact the qubit. And then we see the qubit frequency or the T1 or the T2 times changing. There's some interesting dynamics. One can also do a correlation analysis, so look into the changes of the dephasing time as function of the qubit frequency changing. And at times there's a positive correlation, at times there's a negative correlation, and other times there's actually no correlation. So it is a rich system of physics to explore. Now, in our particular example, the TLS we had was sitting somewhere near the junction. Wasn't in the junction because the coupling was too weak, but it was somewhere nearby the junction. And this is a major and typical source of decoherence. So atomic defect systems which kick the qubit once in a while and then require a calibration or recalibration process of the quantum bit. Let me skip that. I would like maybe speeding up a bit. So a lot of our work is also on hybrid quantum systems, where we couple a superconducting qubit to a ferromagnetic system, which requires some background magnetic field, some static field. So a while ago, we were interested in probing our qubit, actually that particular qubit I just introduced, in a magnetic field, in a static magnetic field, and then ramping up the magnetic field, sweeping the magnetic field, and seeing how the coherence and decoherence of that qubit happens. Now, in this qubit, we had aluminum junctions coming from shadow evaporation. That actually meant we had two junctions in parallel, a big one and a small one. Typically, the large one, which feeds back to the titanium nitride capacitors, doesn't really matter, and you don't see it. However, if you apply magnetic fields and when you suppress the critical current in the smaller junction, or first actually in the larger junction, and then later in the smaller junction, you start seeing this, and this gives rise to these Fraunhofer pattern. If you plot the qubit frequency as function of the outer magnetic flux, you see some oscillation as function of flux, which you wouldn't expect for a single junction. It shouldn't oscillate, and not particularly not at these field strengths. So you can actually use this to learn a bit more about your circuit and about the effective sizes and dimensions of your junctions. Um, I want to be quick on that one. We set up a numerical model to capture the dynamics of these two junctions in parallel, applied that to our data, fitted really well. We've taken the here you see plots of the qubit frequency and the resonator and qubit coherence as function of magnetic flux. And it kind of works well for magnetic flux up to 20 millitesla. But if you go to larger fluxes, or if you keep cycling the magnetic flux back and forth, so do up sweeps and down sweeps, then you start adding more and more vortices onto the system, and overall the system becomes hysteretic, and the coherence is degrading. And it doesn't really work if you go to higher fields, such as 40 millitesla or above. And this is predominantly given just by using aluminum, which is known to have a low critical magnetic field, a low HC. So it's very easy to suppress superconductivity in these thin film aluminum films. Okay, now moving on, this magnetic field dependence and also the existence of two-level systems and the decoherence they bring to the qubit. That was a motivation for us to look into different types of junctions by using by moving away from shadow evaporated junction technology to a more CMOS compatible process based on liftoff, and also to move away from aluminum into other superconductors such as niobium. Now in this work here, we used aluminum, still used aluminum, but we used subtractive processing, which meant we deposited our bottom aluminum layer on a substrate. We then formed the bottom electrode, brought the system back into the vacuum system for ion milling, formed the junction, and then deposit another layer on top, which was again patterned and etched. So to form these overlap tunnel junctions, you see a zoom in here. This is fully CMOS compatible because it doesn't require liftoff and it can then also be brought to higher temperatures if required, because again organics are involved during the deposition. Here's the time resolved data, the T1 and T2 times, and these were up to about 20 microseconds for our device. Now, in the meantime, this process has been actually perfected by IMEC, and I think there's a similar work by Fraunhofer as of this year, and they show coherence times. There's a very similar process, also subtractive processing, of 100 microseconds or more. So, and the IMEC work in particular is coming out of a 300 millimeter CMOS line. So that's it's quite impressive. In Glasgow, we didn't really focus much on the aluminum overlaps. We were more interested by different higher gap superconductors. And about 2 years ago, there was very interesting work coming out of Chicago. Well, it's now, I think, Stanford, but David Schuster at Chicago at that time. He showed work on a tri-layer niobium aluminum oxide niobium qubit. Here's a cross-section we've taken on our device, but theirs looks very similar. So it's full tri-layer grown in situ, and then it's etched back with some sacrificial dielectric, which is later removed to form this air bridge for the top electrode. And now using niobium, of course, means one can work at higher frequencies. One can then work at higher temperatures, which will also allow operations at larger magnetic fields. And all of that is very interesting for, for actually our work. So we studied the Chicago work very carefully. We then uh, started implementing it in our own facility in Glasgow. This is the fab process um, for that junction. And these are data sets now coming out of our lab. So we made test resonators and test junctions, test qubits. Here's an SEM image of one of our junctions. You see the bottom no beam. This is a cross section. So this is um, the bottom no beam layer. There's an aluminum oxide layer here, and then on top we have the top electrode. The coherence or quarter factors for the no beam resonators are about 600K, and we've done a number of chips and wafers where we changed the oxidation conditions to really tune in the critical current density or the resistance area product and then critical current density of our device so that we can build qubits with the right EJ product. Um, the qubits are working. Now, the qubits so far had slightly higher frequencies than designed, which meant they were actually almost decoupled from the resonator and were working at really high frequencies, which and then had to tune down by magnetic field to actually enable readout. But then the coherence was a bit shorter because they had such a high flux dispersion. So we are now in the process of fabricating the next run of qubits, which hopefully will have lower qubit frequencies. Actually, I'm looking at time, so it's quarter to. Should be probably coming to an end. I assume I'm looking at Chris. We start a bit later, but
Yeah, so we have 15 more minutes and we should leave some time at the end for questions, but maybe 5 or 10 minutes,
okay,
depending on.
okay, that's fine. So I will talk about nanobridges and then maybe skip the last. So nanobridges are interesting. Well, for us, they're interesting because they can be built without any dielectrics. That means we can actually avoid well, dielectric materials, which are known to have two-level systems. And there are different types of nanobridges to form junctions. These can be normal metals, these can be semiconductors. To form qubits, one need one needs chosen junctions with critical currents less than a microamp, um, probably more like 100 nanoamps or less. And that by itself, it's a challenge because typically a nanobridge would have critical currents in the order of milliamps. They tend to be strongly coupled. They also have a low self-capacitance, which would make it very interesting to build, say, um, paraamps or tunable resonators or actually qubits where you don't really add capacitance through your junction. Now, we started working on nanobridges about 2 years ago and first did more numerical work. So we are interested in setting up a realistic model for nanobridges. Um, and that didn't really exist, or it existed within limitations. So the student um, well took the Sadel equations and dirty limit, assuming diffusive transport, and then set up to solve a full 3D system with realistic geometries and boundaries without any simplification of layout. And here's a device we also started building. And the model, we then actually took our numerical model and we looked into published data because we didn't have nanobridges at that time. So the data we've taken is work done by Irfan Siddiqui's group about 15 years ago, VJ. And we looked into their junctions, the experimental data, and the critical current predicted by various models like the Kulik and Lanchuk model for planar junctions or very thickness junctions and some other models. And now ours is the star here. And we seem to capture particularly VJ's junctions really well with that model, so within 5%. We can also calculate the current phase relationship, which is key because it drives anomalisticity for superconducting qubits. It should be as sinusoidal as possible to get the best the largest anomalicity. So we have a numerical model which we think captures actually realistic nanobridges quite well. The very thickness junction seems to be the right choice to build nanobridges which have both a high anomalicity and also small enough critical currents. And that's what the student is now doing. So he's fabricating nanobridge devices. He has some of the latest data. So the larger devices have critical currents in excess of 30 microamps. It's too large, but on the same chip, there are smaller and smaller junctions, and he's approaching or actually touching 1 microamp critical currents on the latest run. So, and I should say this has been fabricated on a previous chip before. So it seems we have now a fab process to reproduce small critical current nanobridges, which we'll now probe and integrate into qubits. Being mindful of time, let me just show you 2 more slides. So coming back to the numerical model for nanobridges, this can also apply it for encapsulated resonators. And now this refers to work coming out of SQMS at Fermi level, at Fermilab, where they had used a no-beam resonator and encapsulated that one to avoid the formation of surface defects and therefore improve the resonator quality factor. Now, if you encapsulate the resonator with a non-superconducting material, you might actually form low gapped states at the within the encapsulation layer. Now, with our model, we're able to simulate the energy and gap distribution across the encapsulated resonator. Now, this is actually these are our simulations, but based on the published work from coming out of SQMS. I think all the resonators that they're made are fine, but you see that, for example, using gold as an encapsulation on niobium means you end up with really low energy gaps at the outer edge of your resonator, which means you could have some quasi-particle formation there. But if you take, for example, tantalum around niobium, so you have these 2 superconductors, and then of course you maintain a high gap, which would make it easier to avoid the formation of quasi-particles. You can also use that model to calculate the change in kinetic inductance, which actually Fermilab hasn't studied. But as you build resonators and you start encapsulating them, you would change the kinetic inductance of these resonators if they have some. And that means you would change the resonance frequency, and you would need a numerical model to study that. So we think our model allows that. It also allows to calculate the superconducting gaps when adding quasi-particle traps, for example, in circuits, or to use it for our tri-layer junctions, which are sketched here. So with this, Chris, I would like to finish my presentation. I wanted to talk about some interfacing work where we use photonics and wireless and also cryoelectronics, but I don't think we have time, so maybe another time. Thank you.
Okay. Sounds good. And as we talked about before, if you're ever out this direction, of course, it would be great to have you come by and hear a little bit more about other kinds of work happening there. So thank you very much for the talk. I want to see if there are
Thanks.
any questions in the audience. If so, please go ahead and unmute yourself. And Katie, go ahead.
Sorry, that was meant to just be a clap, but thank you. Yeah.
Okay, that was not a
Okay.
raised hand. That was a clap. Thank
I
you
would
for
like
that.
to acknowledge actually my team. So you see them here. I mean, clearly the team, the postdocs, PhD students, former students, very important. And just a quick summary. Thanks.
All right. Questions, Ravi?
Yeah, thanks, Martin, for the great talk. I really enjoyed that. A little bit on the encapsulation modeling.
Yep.
Have you looked into the differences if you're encapsulating just the top surface versus the top and the edges of the superconductor, and how big of a difference that makes?
No. Um, well, I would get, okay, this is also not for scale. So the thickness is somewhere, right, that's 100 nanometers or something. So if you just encapsulate the edge, then that's a tiny portion. Most of the encapsulation is sitting on top because you do have micron, sorry, okay, now this is, okay, this is numerical work. It says 200 nanometers. Yes, I think that's actually right. That's the simulation we've done, but the actual device had um, micrometer width. Um, so we've done this to actually capture the dynamic, the edges or the um, proximity effect at the edges, or at the edge of these resonators better.
And does it seem to make a pretty large difference? How important are the edges?
Well, so I think on actual device it wouldn't matter so much because you're just encapsulating a tiny part of the entire cross section, right? I mean, you do have 3 cross sections, or 4 if you take the substrate, include the substrate, but then if you just have the 2 edges and the top one, you just encapsulating the side. I mean that's maybe the part where most of your losses are, the TLS losses, as you're etching down your resonator. But it would probably have the smallest impact on the kinetic inductance.
I see. Okay, thank you.
Thanks. Other questions? Either in chat or just go ahead and unmute yourself.
I actually have another one if there's no one else. What frequency were the resonators that you showed for the high frequency niobium? When you had the high frequency niobium qubits,
Yeah.
how high frequency were the resonators that you showed the Q
Um,
numbers?
Standard. I mean, that was, I don't remember exactly, but a few gigahertz, maybe 5, 6 gigahertz. I mean, also driven by our circulators and by the Hempt setup. So we are interested in moving to higher frequencies, but actually the circuit here was designed to operate at a few gigahertz conventionally.
I see. Okay, understood.
You would need to change the entire readout system. I mean, using
Yeah,
different circulators and Hempts and also readout electronics to probe that
right,
outside.
makes sense.
Yeah.
All right. Others? All right. Well, that does bring us just about to the end of the time. So I want to thank Martin again for the excellent talk today. I don't know where the emoji is, so I'll just say it. Thank you very much. We appreciate your time and joining across time zones. And I think we will end the colloquium now.